Ryan Reynolds is behind you. Well, almost. You must be wondering what I mean by that. You just checked and he wasn't there. And why am I saying almost? Well, it's simple. No, I'm actually lying. It's quantum mechanics, so it's very complicated. I'm kidding. But it is quantum physics. But don't worry, I'll explain it in a way you will understand. We all know walls, right? You have a home, hopefully with walls. You might have noticed that you can't walk through the wall. You might think it's impossible, but actually you're just unlucky. There is this thing called wave-particle duality. Sounds complex, but it's simple. When you look at a particle, it behaves like a solid object, like a real ball. But the moment you turn around, that damn backstabber starts acting like a wave. And the funny thing is that when you don't look at the particle, it doesn't have a position. It just has a probability of being somewhere. When you don't observe the particle, it's like letting go of a balloon in the middle of a dark room. You don't know where the balloon is, you just know it's somewhere in the room, and the further you go from the middle, the less likely you are to find the balloon. You only know where the balloon is when you turn on the lights. Particles are the same, except they literally don't have a position when the lights are off. In a sense, it exists everywhere in the room with different probabilities, until the lights are turned on. Now you can think of the balloon as a particle. And the particle has this thing called wave function, which looks dramatizing, but it actually just tells you the probability of the balloon being here or there. We call turning the lights on as collapsing the wave function. Again, sounds complicated, but it actually just means that where there earlier was a chance of a balloon, you now know if the balloon was or wasn't there. You don't always have to light up the whole room, you can just shine your flashlight into a corner. In this case, you either find the balloon, which collapses the entire wave function, or you discover that the balloon isn't there, which also collapses the wave function, but only for that corner. This wave-particle duality makes a lot of weird stuff happen, like it changes the color of your socks. That's getting too complicated, so let's just move on. Cool. But the electron can't escape the room, right? Wrong! So it turns out that the wave function, the math that tells you the probability of the electron showing up, does not end on this wall. The wave function goes inside the wall. And inside the wall, the probability of the electron being there gets cut in half the further you go into the wall. And as some of you might know, if you keep cutting something in half, you never get to zero. What this means is that the wave function never goes to zero inside the wall. It just gets smaller and smaller, but it always manages to stay above zero. And at some point, it's gonna reach the other side of the wall. And this literally means that there is a possibility that the electron will show up in the other side of the wall. This is what we call quantum tunneling. People often use an example where there is a mountain and a ball. By classical mechanics, if you roll this ball without giving it enough energy, it will not reach the other side of the mountain. But in quantum physics, the ball turns into Bob the Builder and digs a tunnel through the mountain and ends up on the other side. Quantum tunneling. Now, it would be almost illegal to not include Heisenberg's uncertainty principle in this. Remember what I taught you last time. The better you know a particle's position, the less you know about its energy, and vice versa. What this means is that if you tried trapping something like an electron into a box that perfectly fits it, you would know its position almost perfectly. But for this current, rules are more important than common sense, so the electron suddenly has more energy than it's supposed to, because we should have no idea about its energy after we discovered its position. So this extra energy lets it roll up the mountain and end up on the other side. So finally, Ryan Reynolds is behind you. You might already see where this is going now. So if Ryan Reynolds is sleeping alone and no one is observing him, or in other words, no one is observing the particles that make him up, the particles technically exist everywhere as a possibility, like in the balloon example. This means that there is a very slim chance that the next time you look behind you, the wave function of Ryan's particles collapse and Ryan shows up. The wave function tunneled through everything in this way, and now there is a chance that Ryan Reynolds will show up behind you, or behind me, or in the other side of the galaxy. The wave function is non-zero everywhere in the universe. The particles that make Ryan up exist everywhere, in every possible order, as a chance. And it's important to note that this isn't my idea. This is a widely accepted part of quantum mechanics. It's as valid for me to say that he exists behind you as it would be for me to say that he exists in his bed. I can only say that it's more likely that you will find him from his bed and not behind you. And unfortunately, the chance of Ryan appearing behind you is so small that every calculator would tell you it's zero, because they can't physically calculate such a small number. This guy explained absolutely perfectly how unlikely it is for a single particle to tunnel through a desk, so go watch that video after this one. And if you remember the flashlight example, you might already know that Ryan can't appear into your room as long as you are observing the room after you observed it the first time and he didn't show up. That's because the wave function of Ryan's particles collapsed in your room once, and they will stay in the same state as long as you keep observing your room. That's all. See ya.